Welcome back. Today is the last session in this module, and today we'll be covering the rest of I/O interfacing. So in this we'll be basically concentrating on 8255. Before we go for 8255, let us see what we have used for I/O interfacing in last class. We had used 373, which was a latch for driving output devices. Let us say you have an LED. To drive these LEDs we were using 373, and as we know this is unidirectional. It will just latch in the data and that will be there at the output. For input we had 244. This is your buffer, and the data from the switches is taken by this 244, and it provides the driving capability. It gives the enough sufficient current to drive the database of your 8086. So we had two devices or ICs. One is 244, that's your buffer, unidirectional from input to 8086. Then we had a latch 373 for 8086 to output devices such as LEDs. As such, the decoding method, we had used two methods. One was using logic gates, and using the logic gates you could do absolute decoding or partial decoding. Apart from the logic gates, we also had the buffer, that is decoder IC, that is 138. And this 138 it has 8 outputs, and we could use each one to enable one of the devices. And this covers both address decoding for both the latches as well as buffers. These latches and buffers are hardwired. 744 I cannot use it as a latch, I can use it only as an input buffer. Similarly, this 373 I can use it as unidirectional, that is, it is used with output port. This cannot be used with input port. 244 can be used with input port. To have more flexibility, and we use 8255. Not only more flexibility, we get more input pins. This 8255 is known as PPI, that is parallel peripheral interface. In this 8255 you have 24 I/O pins. These 24 I/O pins are grouped into 3 ports of 8 pins each. The ports are labeled as port A, B and C. One advantage is each port can be dynamically changed. Port A can be input or output. Similarly, port B can be configured as input or output, and so on. Whereas the 244 and 373 which we have seen previously, they are hardwired, they cannot be changed. But still, whatever flexibility we get is limited. Port A, if I configure as input, the whole 8 pins are configured as inputs. But in the latest microprocessors and microcontrollers, each pin of the port can be configured separately as input and output. But that's a different issue. So here we are in 8255. 8255, there are 24 I/O pins, and in these 24 I/O pins you have 3 ports. Now this is your block diagram of your 8255 40 pin IC. In this 40 pin IC, 24 are your I/O pins. Okay, these are PA specifies port A, then PC specifies port C's, then PB specifies port B. Apart from this 24, you also have some control signals like read bar, then VCC, ground, then data pins D0, D7. This data pins D0 to D7 are used for connecting to microprocessor. Then the features, as I said, it is a 40 pin IC. Then in that 24 pins are grouped as ABC, and we have seen that A can be an input or output, and you have 2 more modes with A, totally 3 modes. One is a simple input or output port. It can also behave as an input or output port with handshake signals. That is, you can get a ready, interrupt, all these signals. Based on this, data transfer can take place. And it can also be programmed as bidirectional port. For the handshake signals, etc., it will be using some of the port C pins. Port B similarly can be programmed as input or output with or without handshake signals. Here we will be covering only without handshake signals, that is plain mode 0. So port A mode 0 and port B mode 0 we will be covering. Port C can be divided into two ports, upper part PC4 to PC7, lower part PC0 to PC3. Each can be programmed separately as input or output port. Apart from this, port C has extra flexibility. Each pin of port C can be set or reset to generate the control signals, and that can be used for generating a square wave or switching on and off an external I/O device. For many purposes, only one pin at a time can be used separately. So you can say in general port C has more flexibility compared to port A and B. One thing is it can be divided into two 4-bit ports. Each one separately can be configured as input or output, and one line of port C can be set or reset individually. So this is your 8255 block diagram. As I said, out of the 40 pins, you have D0 to D7 8-bit data bus that is used for communicating with your processor. Then you have the control signals reset, read and write bar. Then we also have the chip select and address select, that is CS and A1 and A0, and 24 I/O pins. The chip select is along with A1 and A0 are used to select the ports. We need 4 addresses, one for selecting port A, one for selecting port B. So when port A is selected, the D0 to D7 whatever data is there, it will be routed to port A if it is output port. If it is input port, from port A the data will be routed to D0 to D7. Whether it is output or input is decided by read bar and write bar. This read bar and write bar will be connected to memory read and memory write if it is in memory mapped I/O. If it is in I/O mapped I/O, the corresponding signals are I/O read and I/O write. The chip select is used to select this chip. If this chip select is 0, only then this chip is selected, and in this chip which port is selected depends on A0 and A1. If there are 00, port A is selected. If there are 01, similarly port B and port C. Apart from these three, we also have one more register known as control register inside this 8255. What is the job of this control register? Before we start using these ABCs, we have to write into the control register a word. We'll call this word as control word. What is the job of this control word? This control word specifies how the port A is. Is it an input port or output port, etc. And to select that control register, A1 and A0 are 1, 1. So totally a minimum of 4 addresses should be allotted to 8255. Previously we have seen when we are using 373, only one address was sufficient, or 244 only one address was sufficient, because we are using either one buffer or one latch, only one input device or output device. But here we have 3 ports plus control register, so we need 4 addresses, and the 4 addresses are controlled by A0 and A1, 2 address lines along with chip select. And just recapping, you select the port or control word register and direct the data that is there in D0 to D7 to either the port or the control register if it is write bar. If it is read bar, from the port to D0 to D7 is taking place. Once again, that also depends on what is the address pin status here. So this is just recapping. This is read bar and write bar, both are active low inputs. They are connected to memory read or I/O read, and write is connected to I/O write or memory write, depending on whether it is I/O mapped I/O or memory mapped I/O. Then we also have one more pin, that is your reset pin. It clears the control register and all the ports are initialized to input. We have just seen how CS does. CS selects the whole chip. It should be active low to enable the chip, and A0, A1 to select the specific port or control word register. So as we said, let us have a little discussion on control register. This control register is an 8-bit register. Its content is called as a control word. This has the control over all 8255 operation. It's basically divided into two groups, group A and group B. So this is your group A and this is your group B, and in your group A it has port A and port C upper, and in group B it has port B and port C lower. So group A has port A and port C upper, PC4 to PC7. Group B has port B and port C lower. First bit D7 selects the IO mode. So if it is 1, it is IO mode. If it is 0, it is BSR mode. We'll come to BSR mode later. So in the IO mode, each port, let us say port A, I have to select it as an input port, then this particular bit D4 should be 1. If I have to select it as output, this bit should be 0. Remember, input INPUT, the first one is I is 1. Output OUT, so the O stands for 0. So to configure as input, put a 1. To configure as output, put a 0 for port A. Port A has 3 modes. The basic mode is mode 0, simple IO mode. Then we have mode 1 with handshake signals. That's for using for ADC data transfer, etc. Then the mode 2 is for bidirectional data transfer. When you have to communicate between two 8-bit processors, you will be using mode 2. But in this class, we are concentrating only on mode 0. Similarly, port B is having 2 modes, that is mode 0 and mode 1. And once again, port B can be configured as either input or output. The remaining is port C. Port C is divided into 2 ports, 2 parts. Port C lower, once again 1 or 0 for in or out, and port C upper, that is your D3 bit, that's again 1 or 0. Then we have the BSR mode. In the BSR mode, it can be used irrespective of IO mode. First, let us say we use the IO mode. We set port A as input, then port B as output, then port C as I or out, whatever we set. Then next we can use separately the BSR mode. The BSR mode also writes into control word register. And in this one, the D7 is 0 for BSR. BSR is bit set reset mode. So D7 is 1, it is IO mode. And if it is the D7 is 0, it is BSR mode. The rest of the bits D0 to D6 will have a different meaning. In BSR mode, these 3 bits are unused. The last bit, if you want to set, it is 1. If you have to reset, it is 0. Whichever port C pin we want, let us say I want port C pin 2, that is your bit 2. Then these 3 bits D1, D2, D3, you set it as 0, 1, 0. If you set it as 0, 1, 0, PC2 is selected, and if I put a 1 here, and then this word, if it is returned to control word register, immediately port C, the second bit, will be set to high. In the same way, we can generate a square wave using BSR mode, wherein I keep toggling this bit. First you make it as 1, send it out to port C, wait for a small time delay, then make this as 0, again send it out to port C. Keep repeating. What will happen on this bit 2, we have it as a high and low. Now this is your basic circuitry wherein we are interfacing the 8255 to 886 or x86 processors. So we need the 2 control signals, write bar and read bar. As I said, this will be connected to memory read or memory write, or IO read or IO write, depending on the mapping. Then we have the address decoding circuitry. The address decoding circuitry can be using a NAND gate or a decoder. And to this address decoding circuitry, just check all the control, all the address lines are not given. Only A2 and the rest are given, whereas A1 and A0 are given directly to the chip. And we have a latch here. This latch is enabled by ALE, so that address latch enable. When this pin from 8086 goes high, whatever address is there on the multiplexed address data bus is latched into it, and that latched data will be decoded by this decoding circuitry. And in the latched data, we are not taking all A0 to A7. Only A2 to A7 is fed to the address decoder. 2 bits, that is A0 and A1, are fed directly to 8255. We have seen in last slide that A0 and A1, if they are 00, the port A is selected, and so on. The data bus, whatever data is there, that's a bidirectional data bus that is connected directly. And we also have the 3 ports. Then this output of the address decoding circuitry is given to the CS bar. So as I said, this address decoding can be done through a logic gate or a decoder IC. So if it is through a logic gate, a simple example, interface 8255 with 86 microprocessor for a base address of B800. A base address of B800 implies that port A should have 00. The last 2 bits, A1 and A0, if they are 00, then port A is selected. The next all 3 2 ports and control word register will have consecutive addresses. Port B will have 1, port C 2, and control register 3. So only base address will be given, that is B800. Check whether it's a valid address. Suppose the last 2 bits are not 00, that's not a valid address for 8255. For 8255 we require 4 addresses, and out of these 4 addresses, the last 2 bits, the base address should start with 00. If it is something like 01 or 10, that cannot be the base address. So the 4 addresses for this are, the address range is B800 for port A, port B 01, B801, port C, and so on. We take A1 and A0 connected directly to the 8255. A1 and A0 are connected directly to the 8255. The remaining lines, which are the remaining lines, A2 to A7 here, but here it's a 16-bit address, so the remaining lines are A2 to A15. The A2 to A15 are given through a NAND gate. This is your address decoder, and that is given to the chip select. And when I look at A2 to A15, expand B800. So B is 1011, and similarly 8 is 1 with 3 zeros, then 4 zeros, and so on. So A15, it's high, it's given directly. So A14 is low, so bubble it or inverter. Similarly A13 and 12 and 11 are all ones, so they are given directly, and so on. So this is simple decoding using a logic gate, where the address lines from A2 to A15 are decoded through a NAND gate and given to CS bar. These 2 lines, A0 and A1, are given directly to the 8255. The next thing that we have to find out is a control word. So we have seen how the control word is in an IO port here. So this was a control word we have seen, wherein each bit is assigned some values. So the first bit is IO mode, that is D7 should be 1 for IO mode. So in this example, now this is an example, specific example. I require port A to be configured as output port, port B as input, and then port C 2 paths, lower as input, upper as output. So expand D0 to D7, the D7 is 1 for IO mode. Then we have group A signals, port A mode, 3 modes it can have, that is the 2 bits, simple mode 0, so these 2 bits D6 and D5 will be 0 0, and port A is output, so 0. Then we have port C upper, and this port C upper is output, so that is 0. Then we have port B mode, only 2 modes, either 0 or 1. Here we have simple 0, so mode 0. Then port B is to be configured as input port. So port B, this bit will be 1, and the last is port C lower, and port C lower is input, so that is 1. And group 4 bits together, the control word is 83H. A simple program now. Program the 8255 to get data from port A and send it to port B. So get data from port A implies port A is input, and send it to port B implies port B is output port. In addition, the data from PCL, that is port C lower, is sent to PCU. PCL is now input and PCU is output. And we also have port addresses from 300 to 303 for the 8255 chip. So the data that we get from here, port A input, port B output, PC lower input, PC upper output. Apart from this, the base address is 300. 300 specifies port A. So PA EQU 300. So we can use this assembler directives EQ to specify. So instead of using 300H address always, I can use something like PA or port A, PORTA, complete you can use. Similarly, every time instead of using 301, I can use PB. And PC for port C, that is which is address 302, then control word register 303H. Apart from this, before we use these ports, we have to write into the control word register the control word to set port A as input, this as output, again this as input, this is 2. And just in the previous slide, we have worked out this control word. What is the control word? 83H. We will use this directly here. So the control word equals 83, whereas the control word register address is 303. The first step that we have to do is initialize a control word. So to initialize a control word into the control word register, remember this is a 16-bit address. So if it's a 16-bit IO address, I have to use indirect addressing, wherein DX will have the 16-bit address, move DX comma CWR. CWR here is 303H. So 303, the 16-bit address is moved into DX. Then AL is having CW. CW is a control word, that is 83, that is moved into AL. Now this instruction out, destination comma source, that is the AL contains 83, moved into control word register. As soon as this 83 is moved into control word register, the ports are configured. How are they configured? Port A as output port, that's your latch or whatever, port B as input port or buffer, then similarly port C 2 4-bit ports. Now the first step is get data from port A. To get data from the port A, once again DX address should change. Now it should have the address of port A. Now the port A address is 300, so move DX comma 300H or move DX comma PA. Now this PA EQ, it stands for 300, so 300 is moved into DX. And when I say in AL comma DX, from 300 whatever data is there, that 8-bit data is put into AL register. Now send it to port B. To send it to port B, once again the DX register should now reflect the port B address. The port B address is 301, so move 301 to DX and you say out DX comma AL. AL already has the contents from port A that we are sending now to DX, but the DX is now port B, so the data is sent out to port B. So taking the data from port A, then put it in AL register and through AL register send it to port B. The second part of the question is get data from PCL and send it to port C upper. So to get the data from PCL, DX is moved with port C address in AL comma DX. Entire 8-bit of data is moved into AL, but we want only the lower nibble, that is PCL. For this and AL with 0F. So the upper part, upper 4 bits are masked, only the lower 4 bits corresponding to PCL is present in AL. This has to be rotated left, so PCL has to become PC high. From the lower it has to move to the upper position. So rotate left 4 times. So when you rotate left 4 times, the lower nibble will come to the upper nibble byte. So if you are reading in something like 0, 6, after 4 times rotation it will become 6, 0. And that you output once again on port C, but now the 6 will now go to the output port, that is PC upper. Now this is another example wherein port A is input, port B and C are outputs. Find a control word. So now the control word is then we also have to find the port addresses of all the 3 ports and control word register, and then we also have to program the ports to get the data from port A and send it to port B and C. So the figure is given. From the figure we can decode the port addresses. So as we have seen, A1 and A0 are given directly to the 8255 chip. And how much is that? If it is 00, it will be port A. If it is 01, it will be port B, and so on. So then when we decode this, we can see that A2 is 0, A3 is 0, A4 is given directly without a bubble, so A4 is 1, the rest are all zeros. Similarly, A8 and A9, the last 2 are 1, 1. Club 4 bits together, including A1 and A0 as 0, 0. So this becomes 0, this becomes 1, and this becomes 3. So the base address PA is 310. The rest follows. PB is 311, C is 312, and so on. So from the decoding circuitry, that is A2 to A9, put the values of zeros and ones, and port A's you put the base address on A0 and A1 as 00, group 4 bits together, we get the starting address. The rest of the addresses will be consecutive, that is sequential, 311, 312, 313. And we can see that this is IO write and IO read, this is IO mapped IO, and the D0 to D7 from the microprocessor is directly connected to D0 to D7 of 8255. Then we also have AEN, address enable. This bit along with the rest of the address lines enables the chip select. Then we have to find a control word. So control word is for port A as input, port B and C as output. So port A, once again D7 is IO mode, so it is 1. Port A mode 0, 0, 0. Its input, so it is 1, then port C upper output, so it is 0, and rest on it. Port B mode 0 and output, and port C output. So the third part is program the ports to get the data from port A and send it to port B and C. And so this remains the same. Then DX with control word register address, that is 313. Then control word is 90. When we expand this, we had got 90H. So that 90H is moved to AL, and from AL to DX. Get data from port A. So DX is with port A address. In AL comma DX, from DX the data is moved into AL, and that we have to send it to port B and C. So just change DX to reflect port B address, then an out instruction. The AL is from the port A contents, that's moved to port B. Again change the DX to reflect port C address and send the same data. This is another example where it has a base address 300H. So for this base address 300H, expand 300, 3 is A8 and A9, A8 and A9 along with the address enable, then the rest are all zeros and including A0, A1 connected directly. So this gives you the port address of 300 to 303. We also have a special port, that is port 61H, and this port 61H can be used for time delay generation. There are two methods of time generation. Either I can use on-chip timers, that is 8253 or 54, or I can use a delay program wherein I have to work out the time cycles taken for each instruction, which is quite variable. Or I can use this port 61H, and it works with any computer, 286 to Pentium with any clock. The advantage of this port 61H is it has 8 bits, and in that 8 bits the D4 bit changes its state every 15.085 microseconds as long as the computer is on, and this can be used as a standard time, and we can use it for a time delay generation. The other methods of programming the timer or writing a delay program is quite lengthy and it may not be so accurate. The best way is to use port 61H, and at the D4 bit we keep checking out how many times it has changed its state. Every time for it to change its state, it takes approximately 15 microseconds. Multiply that how many ever times we want to generate whatever time. So this is an example wherein we are toggling all the bits of port A continuously, and we are checking if there is a key press, you stop the program. Key press from the keypad is checked with this int 16H. And once again we have the control word as 80H to configure all of them as output ports. Then control word is moved into control word register, that is 303. Then move DX with port A address, that is 300. And for toggling, last time we have seen the pattern 55 and AA. So 55 will make all odd LEDs high and even LEDs low. Similarly AA, the reverse will take place. So move AL with 55, out DX comma AL, DX is port A. So 55 is moved to port A. Then call delay, and then again we are changing the pattern from 55 to AA, alternate pattern. Same thing, we are sending it to the output and call delay. For this 55 and AA, check the last presentation we had done, then call delay. Now you check before repeating whether any key is pressed. For this we have to use a DOS interrupt with the AH as 01 function, int 16H. So if there is as soon as this is executed, it will check whether any key is pressed on the keypad, and if there is no key pressed, the 0 flag would have been set. If it is 0 flag is there, again go back and repeat. Again that AA you make it as 55, then delay, then again AA and delay. You keep repeating until a key is pressed from keypad. As soon as a key is pressed from keypad, exit from the program. Then come to the delay procedure. We had a call delay here. As I said, for the delay procedure we can use port 61H. So save AX contents, whatever the AX contents are, just save it on the stack, and then move how many times we have to do the counter with this sum number. And how do we get this 16,592? If I multiply 16,592 into 15.085 microseconds, I get a quarter second delay. Similarly, if I double this number, we will get half a second delay. So take the time that is required, let us say 0.25, divide by this 15.0585 microsecond, I get a number. That number will be moved into CX register. Then input AL comma 61H. From 61H, the 8 bits of that 61H is moved into AL. We have seen in the 61H, out of the 8 bits, the 4th bit changes its states every 15 microseconds. So mask all the bits, keep only the 4th bit, that is D4. So D0 is 0, D1, D2, D3, all are zeros, only D4 is 1, again the rest are all zeros. When we AND it, only that will be left. If D4 is 1, AL will be 1. If D4 is 0, AL will be 0. Now compare AL with AH. Initially AH can be any value. So when we compare it, there are chances that they are not equal. If they are equal, you have to go to W1. If they are not equal, what do? This whatever status of this AL is there, move to AH, then pop AX and return. Else what do? We also have a loop instruction wherein we are this is your CX, so jump on equal to move, then between pop AX and this there is one instruction, that is loop W1. So what does this loop W1 do? It will repeat this CX times, So one instruction is missing before pop AX. That instruction is loop W1. So next time it comes here, the state here, it will continue, and as soon as the state is continuing, AH and AL will be the same. So it will keep waiting till the state changes. If D4 has become toggled from 1 to 0, AL also will toggle, and when I compare AL with the previous state, there is a change of state. So it will not come to W1, rather the current state will be moved to AH, current state will be moved to AH, and then that loop will decrement CX, and again it will go back to W1. So how does this work? So get the current state of D4 by masking it, put it in AL and check with AH. So first time AH can have anything, so it will not execute, rather the current state will be put into AH, and again it will come back into the loop, and it will check whether it is the same state. Compare AL with the stored state. If it's the same state, it will keep waiting in the loop. As soon as the change state is, it comes out, moves the new state to AH, decrements the CX count, and if it is not so, it keeps repeating. So this will generate the required delay of half a second or quarter second. Then we come to the next concept of buffering IO address ranges. So let us say I have a system bus. In the system bus, I have provision to plug in many cards. Each card, if I plug in, I have to allot certain addresses to this. For example, in this card, if I plug in 8255, I have to allot 4 addresses for 8255. Remember, 8255 has PA0 to control word register. 4 addresses has to be allotted to 8255. Similarly, any other device you connected into the plug-in card, we have to allocate certain ranges, so that and these ranges should not overlap. To take for that example, we have 2 methods. One is using a bidirectional latch like this 245, and then this latch is enabled only for certain range. And this is an example wherein whatever devices are connected to this 245 will work only in this range, 300 to 31F, and the other range these devices will not interfere with. So for 300 to 31F, you have the start address and the end address. Once again, 300 expand and 31F you expand. So when we see this, we can see that A0 and A5, A0 to A4 are changing. A0 to A4 for start addresses are zeros, and for end address A0 to A4s are all ones. So you don't use A0 and A4 here. The rest of them, A5 to A9, which are fixed, give it directly to the address decoder, and that will go to the enable of the latch. So only for these ranges, that is 300 to 31F, even if A0 to A4 changes, the device that is connected here will be enabled. Apart from this range, this latch will not be enabled, and you have protection. Another method is used to use the decoder, and we are seeing as usual with the decoder 8 outputs, Y0 to Y7. Let us take an example. Suppose if it is Y0, for Y0 the ABC should be 00. So if the ABC is connected here, the ABC is connected to A2, A3, A4, so they are 00s, and then we have A5, that is active low, G2, so it should be 0. Then I have again G2B, that's active low, and we can say anyway NAND gate directly active low. To enable the active low, A6, A7, 00. And what about A8? It is 1, A8, 0. And again the enable, address enable, that is not shown, but the rest are shown. Expand this, we get the range. Along with A0 and A1, the address range is 300 to 303 with Y0. So Y1 has a change in this ABC. So the ABC will be 001, and when we group it together, it will be 304. So this is 3, A9 and A8 is 3, then 0000, 4 zeros, there's a second one, and then 01, then 00. 0100 is 4, and then 01, and these 2 bits are 11, so 3 ones it is 7. and the same lines you can expand, and you can check out that different address ranges are given for selecting different outputs of the decoder. And this is your bus expander, where you can see that the decoder output is taking each one, whether 345 or 344, all are enabled through this decoder. So once again we have a program to toggle all bits. Once again, use half a second delay, use 16H. So this you can just go through. That's your control word register, then 355 delay, and then again A, then a delay, check for key press and exit. Then you have a delay procedure. Here also one instruction is missing, loop W1 here. And you have other examples like interfacing, generating a square wave using a DAC interface. For example, these are examples just to show you how the 8255 can be used with the output or input ports. So for example, if you have to interface a DAC, an 8-bit DAC, complete one port A is used, and on the port A you send 00, the DAC output is 0. Send FF, that is D0 to D7 are all 1 1, it will generate 5 volts. So alternatively generate 5 and 0, with the delay a square wave is generated. If you want a triangular wave, you keep varying from 00 to FF. You keep incrementing, so the up wave of the triangular wave is there. Once it comes to 5, again you keep decrementing, so you get the down wave of the triangular wave. That's your D2 loop. D2 loop takes care of the down. Then an example, stepper motor. Stepper motor does not require a complete port A. Only half of port A, let us say PA0 to PA3 is required. Only 4 bits are required for the stepper motor. And we initialize the pattern, let us say 11 or whatever. And then we keep rotating the pattern and the stepper motor moves. Then we come to I/O programming in Visual C and C++. So when we are having Windows, and in Windows we are using Visual C or C++, as we know it's an object oriented language and it has many classes and objects. This makes the programming easier and more efficient. But the problem with this Visual C and C++ is there is no class or object to directly access the I/O ports, especially in the Windows version. And why did Microsoft do this? So this is ensure that x86 programming is under the full control of operating system, and it precludes any hacking into the system hardware. Especially for Windows NT 2000 XP and higher, you cannot have direct access to the I/O ports, and not only I/O operation, then in and out instructions. The DOS interrupts in 21H also cannot be accessed in Windows XP and subsequent version. You have to buy the Windows platform SDK through the starter development kit provided by Microsoft itself. Only through this environment you can control the I/O devices. And when we are controlling through this I/O devices, what are the input and output instructions that we can use? In this is not a problem in lower versions of Windows like 95 and 98. We can use direct I/O addressing. Only the DOS interrupts are not available. So most of the 86 programming, when we do from Windows, we go to the DOS environment, and in the DOS environment we use it in 21H or in 16H, etc. So most of the programming for 86 is done in DOS environment. But if you want to use Visual or Visual C++, we have to go to the console mode, and in the console mode we have to use different instruction syntax, and the syntax generally has an underscore. And apart from this, there are also other differences. In the basic ALP of 86, you have a difference between an 8-bit I/O address and a 16-bit I/O address, whereas in Visual C++ there is no such distinction. All are taken as 16-bit addresses. So coming back to the differences in 86 assembly language programming, if you do it on DOS platform, we have out port number, that's your 8-bit number, comma AL, that's your direct addressing, or in AL comma port number. And if you have 16-bit, we have to send it through DX, out DX comma AL. Whereas in Visual C++, it's only one instruction, underscore out P, and in the brackets you have to give the port number comma byte. This port number can be 8-bit or 16-bit. Similarly in P and the port number, that port number can be 16-bit. So the in and out instructions are given by underscore out P and underscore in P. And this is a simple C++ program to toggle all bits, and we have to use a keyboard hit function to exit if there is a key press. Once again, you have the header files, conio.h, stdio, etc. And initially we set the IO's flag, the buffer, unit buffer. So this this unit buff ensures that the buffer is flushed after each insertion operation. The old ones are not there. And then we also print out, that is program for toggling. This will print it out on the screen, as you know. And first thing that we are worried about is this, underscore out P. The address is 303. 303 is your control word register, and what is the data you are sending? 0x80. That's your control word. Control word is sent to the control word register. Then this do while, this instruction will execute this again and again. However, in the loop, what do we have? 300, we are sending 55. 300 is your port A, and 55 is sent to port B also, that is 301, 55 is sent. Then the sleep instruction executes a delay, and that 500 ensures an execution delay of 500 milliseconds, and then change the pattern from 55 to AA, so that 1 becomes 0 and 0 becomes 1. Similarly both on port A, B, and then a delay. So keep doing it until keyboard hit is not there. What does this symbol exclamatory say? Not. As long as this is not there, you keep executing. As soon as a key is pressed on the keypad, you come out, similar to your int 16H. This is another program wherein you are taking input from port A and sending it to port B and C. So for taking in this, your control word is 90. 90 is sent to 303. You are giving a small delay. Then you are defining one 8-bit, that is your my byte. That your my byte is unsigned char 8-bit. So you define my byte as a user defined variable char, and then my byte is equal to in P, that is you are inputting from port A. That 8-bit data from this is put into my byte, and the same my byte is sent to 301, that's your port B, 302, that is port C. And in between you give a small, and you can also send it to the PC screen, that is C out, then some 2 lines, new lines, and you keep repeating it. Then coming to Linux, so previously we were talking about C programs for Windows. Now instead of the operating system is Linux, and we are using Linux C++. As we know that Linux is also a popular operating system for x86 PCs. The difference here is to compile IO programs, we have to link the library files, that is GCC, this we have to use, and to run the program we should be in the root, or root must change permission so that it comes to this toggle. See on root toggle, and it will come here. Now toggle can be executed by the users. Here we are worried about the in and out instruction, similar to Visual C++. Here in Visual C++ we had underscore out P. Here for Linux we don't have the underscore, rather just that is out P, it is out B here, out B, and byte and port number. Here also you don't make a distinction of whether it is 8 bits or 16 bits. Similarly input INB port hash number. This is an in and out instruction, and a small program in Linux once again to toggle all the bits and check a 500 millisecond delay and a key press. So here we have int n equal to 0, the delay 5 into 10 power 5, that's your delay, and then you get the IO permission for starting from address 300 for 4 locations. You get the IO permissions. Once you get this IO permission, this is your data So here we have the data and then the port. Previously we had the port and the data in visual. So this is your data 80 that is sent to the port, then we are clearing the screen, then we give a delay and we keep checking the print is 55 and on to the 300 port A, the same 55 to port B, that's your out B, give a small delay and keep repeating, change the pattern from 55 to A. Keep doing till you use n equal to get character, that is check whether any key is pressed. As long as it is less than or equal to 0, keep doing this and return. This is another program to send. Here we use in instruction, that is and then in B from port A we are putting in I, and that I we are sending it to port B and port C. So this finishes your Linux C++ programming. And today's class we have finished about 8255. How is it different from your latches and buffer? We have programmable ports here, the control word for 8255, the address decoders for 8255, later the in and out programming in Visual C++ and Linux C++, if that is for Windows and Linux versions. What are the changes in the IO instructions? So this concludes module 3 of your syllabus. Thank you.